Hello and welcome to the channel on engineering education. Our topic for today's discussion is Bloom's taxonomy and how it is applied to a program in electrical engineering. The example that I would quote would be in the area of circuits and systems. So let's begin. Bloom's taxonomy was initially presented in 1956. The aim was to give a structure to any academic program. So Bloom's taxonomy starts with building the foundation first and then builds a beautiful building on top of that foundation. The first level in Bloom's taxonomy is to remember or recall. So certain important concepts are first built, then there's a good understanding of these concepts. Next level is to apply those concepts, and after the foundation is complete, then we move to this analysis of the learning that has taken place so far, then evaluate different options, and the highest level is to design or to create. Let's see how these levels are at play in an electrical engineering program. So to remember is when the student starts a degree program, the student is expected to remember basic concepts of mathematics and physics, such as the laws, Newton's laws of motion, the concept of light, the structure of atom, different mathematical formulations in terms of Pythagoras theorem, trigonometry, differential equations. So a number of these concepts are frequently remembered and recalled, starting from the engineering studies. Then the level is to understand. So student should have a good understanding of different variables and parameters. So a good example would be Ohm's law, where we see the interplay of voltage, current, and impedance. And a good understanding means that then we can derive the relationship of power dissipation from these variables. So student should have a good understanding of different concepts, and once the student is able to recall and has a good understanding, then we can apply those concepts in solving different types of numericals and analyzing simple circuits, such as given voltage and resistance, finding out the current through a certain resistive or resistor, inductor, or capacitive device, looking at the power coming out of a battery, looking at the load that is seen by a circuit, and so these kind of things. So the student can now apply these concepts that were previously understood and recalled. So after this application part, the next higher level is to analyze. So here this becomes interesting, and if you look into an engineering program, a lot of effort is put in analysis. Actually, analysis is one of the strong attributes of any engineering program. This is what distinguishes engineers from some other disciplines of academia. So examples of analysis, there are many, but let us first look into a digital system where the student could be given a digital circuit comprising 3 or 4 flip-flops and some combinational logic. And the expectation is to draw a finite state machine diagram or a state table by looking at this or analyzing this type of digital circuit. Similarly, a complex RLC network could be given, and the student could be asked to determine the input impedance or the impedance by looking at the load for the circuit. So this requires complex arithmetic skills as well as a good level of understanding. So once we have achieved the analysis level, then the step of evaluate comes in. So evaluate is that a number of things have been taught to the student, a number of concepts have been learned in the class and the laboratories, and now the time comes to weigh different options to apply to a certain solution. For example, there are 3 types of amplifiers, or even 4 sometimes. So class A, class B, and class C. So a particular situation demands an amplifier that provides the least amount of distortion. So can the student identify from these three amplifier types and pick one and then use in the circuit? So similarly, a number of possible permutations exist for digital circuits, where a circuit could be built from different types of flip-flops, different types of combinational gates could be used. So what will be the design consideration in those circumstances, and what type of appropriate components would be utilized. So this is the evaluate part. The highest level of learning that is expected in any program is to design and to create. So this practically refers to developing a working engineering system from very high level specifications. So high level specifications could be given the area of a rooftop of a house, devise a photovoltaic solar backup solution that works for 12 hours a day and provides energy at 10 kilowatt hour. So then the student is open for the student to evaluate different options, to analyze different types of solutions, looking at the cost, looking at the implementation complexity, and the type of components that are available, and different types of inverters, and come up with a working engineering model. Similarly, you can ask the student to develop a security layer between your laptop and the Wi-Fi. And then there are a number of solutions that are possible. There could be dedicated chip, a circuit using dedicated chip made on a PCB. There could be a microcontroller that could be programmed with certain peripherals. There could be an FPGA circuit that is made for this type of solution. So a number of solutions are possible, and depending on different constraints, including time, including cost, including the implementation complexity, and the knowledge of knowledge or the capacity available at that particular place, what type of solution and then can be adopted. So this actually completes the full spectrum of Bloom's taxonomy. So I hope you found this video interesting. If you have any idea on how Bloom's taxonomy is applied to your own field of engineering, please write it in the comment below, and we will contact you and ask you for your video that we can use in this channel. So subscribe to this channel if you found this interesting, and we will keep bringing more interesting videos for you. Thank you and bye bye.